Everything you have ever seen drawn about what's under Yellowstone. Every documentary graphic showing a giant column of molten rock rising straight up from deep in the earth. And the team that just built the most detailed underground model of the western United States found something a lot stranger and honestly, a lot shallower. I want to be upfront about something before we get into it. This research does not point toward an eruption happening sooner than expected. If anything, researchers involved describe part of it as reassuring for near-term risk. What it actually reveals is something else entirely, that one of the most heavily studied geological features on the planet has been misunderstood at a basic structural level for 50 years. Before we get into what changed, it helps to clear up a basic misunderstanding a lot of people carry around about what Yellowstone actually is. Yellowstone is not a mountain. When most people picture a volcano, they picture a cone with an opening at the top. Yellowstone has no cone at all. Yellowstone is a hole, a caldera roughly 30 by 45 miles across, so enormous that when you're standing inside the park photographing elk or watching the bubbling hot pools, you genuinely cannot feel that you're inside a giant crater. A caldera forms not when the ground explodes violently outward, but when it collapses downward because whatever was supporting it from underneath has since left. Yellowstone has done exactly that twice over the past 2 million years. Once around 2.1 million years ago, and again roughly 630,000 years ago, with each event throwing out somewhere between 1,000 and 2,500 cubic kilometers of rock, ash, and magma. For comparison, the 1980 eruption of Mount St. Helens, the one that flattened forests and dominated national news for weeks, released roughly 1 cubic kilometer of material. Yellowstone's past eruptions were on the order of 1,000 times larger than that. Anything over 1,000 cubic kilometers earns its own separate classification, a super eruption. The reason these events matter so much isn't really the crater itself, but the ash and sulfur they throw into the atmosphere afterward. Enough to dim sunlight and drop global temperatures for years at a stretch, disrupting agriculture on a global scale. That's the system this new research is trying to understand more precisely. Let's start with what most people already believe about Yellowstone, because that belief needs to get knocked down before anything else makes sense. For roughly 50 years, the standard explanation for what powers this supervolcano was something called a mantle plume. Picture a lava lamp, heat the base, and a blob of hot wax breaks free and rises straight up in a column. The old theory said Earth does something similar, a plume of superheated rock rising from deep near the planet's core, burning its way upward through the crust like a blowtorch aimed at the underside of North America, held under what geologists call a caprock layer that traps the heat until it finds a weak point to punch through. That idea had one huge point in its favor. Yellowstone sits in a genuinely strange location. Almost every volcano you can name sits near the edge of a tectonic plate along the Pacific Ring of Fire. Yellowstone sits in the middle of a continent, 1,000 miles from any plate boundary. A blowtorch rising from deep underground was the obvious way to explain a hotspot sitting in the middle of nowhere with nothing at the surface to obviously account for it. But that theory had a problem, one that quietly bothered geologists for years without ever getting fully resolved. A blowtorch plume predicts a narrow, focused column of heat, essentially a single hot point rising cleanly from below. What scientists actually measure underneath Yellowstone is nothing like that. For years, that mismatch sat there as an uncomfortable footnote nobody had quite enough computing power or data resolution to fully resolve. They just couldn't yet prove what was actually happening instead. So the plume model stuck around, mostly because nothing better had replaced it yet. That finally changed with a new study published in the journal Science earlier this year, led by a research team including geophysicist Liu Laijun, working with the Institute of Geology and Geophysics at the Chinese Academy of Sciences. The team built a high-resolution three-dimensional simulation of the entire western half of North America, modeling both the rigid outer shell of the planet and the slower, softer layer sitting underneath it. Then ran that simulation forward using real present-day physics, cross-checking the results against independent geophysical and geochemical data already collected over decades of study at the site. What came out the other end was not a rising column of heat at all. The heat feeding Yellowstone is not coming up from directly below. It's arriving sideways. To understand why, you need two layers. The lithosphere is the planet's rigid outer shell, the crust plus the very top of the mantle, cold, brittle, and essentially solid. This is what people usually mean when they say tectonic plate. Sitting underneath that plate is the asthenosphere, technically still rock, but hot enough that over long stretches of time, it behaves almost like glacier ice, solid to the touch in the moment. But capable of slowly flowing and creeping over thousands and millions of years, the way a glacier appears frozen in place from one day to the next, but has clearly moved when you compare photos taken decades apart. What the new model shows is that this deeper layer is not sitting still beneath the western United States. It's flowing horizontally, sweeping steadily eastward, moving at a pace of roughly inches per year. Slow by human standards, but massively significant across geological time. Researchers are calling this an eastward mantle wind, borrowing weather terminology to describe something made entirely of slowly moving rock rather than air. What's actually driving that flow is, in a very real sense, a ghost. Tens of millions of years ago, an ancient slab of oceanic crust called the Farallon Plate was sinking down underneath western North America as part of normal plate tectonics. That plate largely disappeared from the surface long ago, but remnants of it are still sinking deep beneath the middle of the continent today, and that ongoing descent is still steering the flow of mantle material above it. In other words, the volcanic system sitting under Wyoming right now is partly being fed by the lingering wake of a tectonic plate that stopped existing at the surface a very long time ago. Here's the part that makes this genuinely clever from a geology standpoint. The flowing mantle rock is hot, but it's not liquid on its own. So how does it eventually melt and feed a volcanic system? The answer isn't that anything adds extra heat to it. Instead, something takes pressure away. Picture a sealed, warm can of soda. It has no bubbles, not because it lacks carbon dioxide, but because pressure inside the can is keeping that gas dissolved in the liquid. Crack it open, and suddenly it foams instantly, without any heat being added and without anyone shaking it. Simply dropping the pressure was enough. Deep underground rock behaves in a strikingly similar way. Under enough pressure, rock stays solid even at genuinely extreme temperatures that would obviously melt it under normal surface conditions. Let that rock rise even a small distance, and the pressure holding it together eases, and it can melt right where it is. Geologists call this decompression melting, and it turns out to be the actual mechanism feeding Yellowstone's volcanic system, rather than a straightforward blast of raw heat surging up from the depths. This same basic process, incidentally, is also what drives melting beneath mid-ocean ridges elsewhere on the planet, so it's not some exotic mechanism invented just to explain. Yellowstone, it's a well-understood geological process being applied here in a genuinely new context. Put those two pieces together. The mantle wind sweeps eastward, gets nudged gradually upward as it moves, decompresses along the way, and starts melting near the top of the asthenosphere, relatively shallow compared to the old Plume model. The furnace powering Yellowstone was never a narrow, mile-wide chimney running straight down to a single deep source. It's closer to a sideways draft of hot rock that partially melts itself simply by virtue of rising as it travels. A genuinely different physical picture from the one taught in classrooms for decades. That eastward mantle wind isn't simply carrying heat along quietly underneath everything. It's physically pushing, shoving against the thicker, colder lithosphere sitting to the east of Yellowstone. At the same time, more buoyant, lighter material to the west is pushing back in the opposite direction. You end up with two opposing forces acting on the same slab of rock from different sides simultaneously, and the plate caught in between gets stretched under that tension. Picture pulling apart a piece of taffy or a stretch of pizza dough between two hands. It rarely snaps cleanly all at once the way glass would. Instead, it thins out gradually in the middle, weakens further as the pulling continues, and eventually tears open along a line where it's become thinnest. That's essentially what this new model suggests is happening to the lithosphere sitting underneath. Yellowstone right now has been happening for a very long time and continues happening today. It's being pulled thin and torn open, and that tear becomes an actual channel, a pathway that lets melted rock migrate upward far more easily than it ever could push through a fully intact, unbroken plate with no weak points to exploit. That torn channel also explains the strange, lopsided shape scientists have measured underground for years without fully understanding why it looked the way it did. It was never a single dot the way heat under Hawaii forms a genuinely narrow, focused hotspot rising from one concentrated source. It's a seam, a long tear stretched across a significant distance in the lithosphere, which is exactly why the heat signature leans off toward the southwest instead of sitting directly beneath the surface as a clean, centered column. This new picture essentially rules out one of the most persistent popular images people carry around about Yellowstone, some enormous underground lake of glowing liquid magma, just waiting beneath the surface. ready to burst forth at any moment. That lake, as commonly imagined in documentaries and disaster movies, is not there, and based on this research, it likely never was in the first place. What sits underneath Yellowstone instead is something geologists call a magma mush. Mostly solid crystal material with pockets of liquid melt sitting in the gaps between those crystals. More like a slushy than a swimming pool or wet sand if the water soaking through it happened to be molten rock instead of water. Critically, you cannot simply drain a slushy the way you could drain a lake, and you cannot easily pump one out through a straw either. It doesn't slosh around freely, and it doesn't surge upward on its own the way a body of pure liquid magma could under pressure. This magma mush is genuinely stiff and resists flowing, its effective viscosity many orders of magnitude higher than that of pure liquid magma, which means it doesn't erupt easily under ordinary conditions, and directly challenges some of the older assumptions about how buoyancy alone was supposed to drive an eruption. A body of truly liquid eruption-ready magma appears to assemble only briefly, shortly before an actual eruption takes place, rather than sitting there fully formed and ready to go for centuries at a time, waiting for the right trigger. So what does all of this actually mean for the risk of an eruption, which is understandably the question most people actually want answered? To be direct about it, this finding does not mean an eruption is coming anytime soon. Researchers involved in this work do not believe Yellowstone is somehow overdue or approaching some kind of scheduled event, and nothing in this new model points toward an imminent supereruption. If anything, the fact that eruptible magma only assembles shortly before an eruption, ready reservoir sitting just beneath the surface, is arguably reassuring in the near term, since it means the system spends the vast majority of its time in a state that genuinely resists erupting, rather than constantly sitting on a hair trigger. But flip that same finding around, and it also introduces a real, uncomfortable complication worth taking seriously. If the classic warning sign everyone has been told to watch for, a giant magma chamber slowly and steadily filling up over centuries, visibly building toward some kind of climax that monitoring stations could track well in advance, simply isn't how this particular system behaves, then the old monitoring assumption may not hold up either, and that matters for how we prepare going forward. Compare this to somewhere like Iceland, where researchers can directly track a magma chamber gradually refilling after each eruption, watching it approach roughly the same volume it reached right before the previous eruption, in a fairly predictable, observable, repeating cycle that gives scientists real lead time. Yellowstone, according to this new model, doesn't appear to work that way at all. Nobody has ever actually observed a supervolcano the size of Yellowstone go through a full eruptive cycle from the outside using modern instruments, so there's no confirmed real-world example to compare this new underground picture against. No template scientists can simply apply with confidence. That's not the same thing as saying an eruption is imminent, and it would be dishonest to frame it that way. It's something quieter, and in its own way more uncomfortable. The monitoring community may have been watching the wrong specific signal all along, based on a model of how the system worked that this new research suggests was fundamentally incomplete from the start. Now, for the part of the story that genuinely made researchers sit up, Yellowstone hasn't stayed in one place throughout its history, and understanding that movement matters for thinking about what comes next. The most important part of this story is not really that Yellowstone is somehow scarier than people previously assumed, because on balance, this research leans toward the opposite conclusion about near-term risk. It's what this reveals about how much confidence was actually justified in the first place about one of the best-studied geological features on the planet. Researchers had already sensed something didn't quite fit about the old description, long before this new model came along to explain why the numbers never quite lined up. Nobody can directly observe the interior of this planet with their own eyes, drill down and take a look, or simply pull up a live camera feed of what's happening miles beneath the surface. Everything we currently know about the enormous machine sitting beneath our feet comes from indirect evidence, seismic wave patterns, mathematical modeling, geochemical sampling, and computer simulation. All of it is necessarily provisional and subject to revision as better tools. A few weeks ago, when this new study came out, the actual physical ground underneath Yellowstone hadn't changed even slightly. Not 1 degree hotter, not 1 crack wider. What changed was the picture sitting in scientists' heads of what's really happening down there. And given how confidently the old picture had been taught for 50 straight years in classrooms and documentaries around the world, that shift in understanding is genuinely worth paying attention to. If you want more real, honest science like this, subscribe and I'll keep bringing you the research as it develops.